Hello and welcome to Honors Function. In this lecture, we're going to be covering an important result in mathematics called the fundamental theorem of algebra. The form in which I'm going to give it to you is the actual fundamental theorem of algebra, the one that was proved in the beginning of the 18th century. There are many proofs for it, but all of them are outside the scope of this curriculum. Very often, though, we remember the fundamental theorem of algebra by its corollary. So, of course, that's going to be the most important result, but the hard one to prove will be the actual theorem. Let's begin. So, for the fundamental theorem of algebra, you need a polynomial of degree n, therefore I have to assume that an is not 0, and all the coefficients, an minus 1, a1, a0, are all complex number. Okay, so this is a complex polynomial. The fundamental theorem of algebra guarantees the existence, there exists at least a complex number z1. It guarantees the existence of a complex root such that p at z1 is equal to 0. Okay, so the fundamental theorem of algebra just guarantees at least the existence of one complex root. That's it. That's all. That's all it is. Okay? Pretty tough to prove. Let's go over the corollary right now. So, if you have at least a complex root, then you can write p of x as x minus this root, right? Times the quotient polynomial, q of x. Okay. Now, q of x, what is the degree of q? Well, the degree of q is, if this has a degree of n, then the degree of q is n minus 1. So q is a complex polynomial, right? A polynomial with complex coefficient of degree n minus 1. Therefore, by the fundamental theorem of calculus, there exists at least a complex number z2 such that q of z2 is equal to 0. Therefore, you can write q as a product of x minus z2 times the quotient of the division. So you're going to have x minus z1 times x minus z2 times another quotient, let's call that q2. Now, it keeps on going, right? Because q2 is a polynomial of degree n minus 2 with complex coefficient. Therefore, you can find a complex number z3 such that q2 of z3 is equal to 0. Therefore, you can factor, and you see where that's going, right? The final result is that you can write p of x as the product of all these linear factor, x minus z1 times x minus z2 times, and how many roots are you going to find? Well, n roots. Okay, now you have to be careful right here. The leading coefficient right here, the leading coef is an, and the leading coefficient right here would be 1, so I have to multiply by an. Okay, but anyway, the main result is that you have n complex roots. Okay, that's really how very often we remember the theorem, the fundamental theorem of algebra. Now, these complex roots, some of them may be the same, okay? Maybe z1 is the same as z2. You're just going to have to repeat the counting, okay? It's not because the root is repeated that you cannot count it twice or thrice or more than that, okay? You need to count the roots with their multiplicity, okay? And when you count the root with their multiplicity, you will find n, oops, there's an s here, n complex root. So here we have to add counted with their multiplicity. Okay, very, very important. If you don't count them with a multiplicity, you may not find n roots. Let's go over another aspect of the corollary about the factorization of a polynomial. This time, I'm going to take a polynomial with real coefficient instead of complex coefficient. I'm going to take a polynomial with real coefficient. Now, of course, a real number is a complex number, right? So if I say that an, a1, a0 are real, if they're real, of course, they are also complex. Okay, therefore, I can apply the fundamental theorem of algebra, and I would be able to write this as the product of n linear factor. So x minus z1 times x minus z2 times x minus zn right here. Okay, so it's almost the same, but this time an would be in R. But that's not what interests me. What interests me, so in this case, all the factors are linear, right? That means they all have a degree 1. But I can also write p of x as the product of some linear factor, a1x plus b1 times a2x plus b2 times, okay, times a r, not necessarily n, okay, a rx plus br times some quadratic irreducible factor. So how can I write that? I'm going to write it as c1x squared plus d1x plus e1 times, and it goes on until let's say cpx squared plus dpx plus ep, and these are quadratic irreducible. That means you cannot factor them with real number. That means their roots, okay, their roots are all complex. Okay, so I'm going to show you how that works, but basically that's all I'm covering in this set of notes. Now, this may be a little bit abstract. You should have seen it last year, but let's go over a few applications. Actually, I'm going to have to, I didn't put enough application there, so I'm going to give you more examples, so please follow along. Let's start with example 1. Describe all the possible types of roots, real or complex, for a polynomial of degree 3. So you take a polynomial of degree 3, so a3x3 plus a2x squared plus a1x plus a naught. Okay, this is a polynomial of degree 3. We're going to assume that a3 is not 0. Describe all the possible roots and give an example of such polynomial. So maybe all the roots, maybe z1, z2, and z3 are all complex. Now, if they're all complex, I know if they are all complex that this polynomial p of x will have some complex coefficient, okay? Because if it didn't have complex coefficient, if all the coefficients were real, we know that complex root comes in pairs. You couldn't have 3 complex roots. You can only have 2 or 4 or 6, but not 3. So if you have 3, that means the coefficients are not real, okay? So for example, we could have p of x equals x minus I times x minus 2i times x here. Let's say x plus I right here. Okay, so x minus I times x plus I, that's x squared plus 1. X squared plus 1 times x minus 2i, so that would be x cubed. Plus, so where's my x squared? I have 1 right here, right? So it's a minus actually. So minus 2i x squared. Where's my x right here? Plus x, and then the constant term minus 2i. So here's an example of a polynomial with 3 complex roots, all different. I, negative I, and 2i, okay? And again, it would be impossible to find such a polynomial with real coefficient, because if it has real coefficient, complex root comes in pair. All right? Now, can you graph this? No, you cannot graph this in the plane that you know, because in the plane that you know, the horizontal line is the real line and the vertical line is the real line. How will you graph this? Okay, so we don't know that. This is a polynomial whose outputs are complex. They're not real, okay? And this is the line of the output, so that doesn't work for this, okay? Now, what about if the polynomial has real coefficients? So let's take a polynomial of degree 3 now. a3x cubed plus a2x squared plus a1x plus a naught. And this time, let's assume that all the coefficients are real, okay? So what's going on here? What can happen here? Okay, all real. Well, you may have how many roots? You may have 3 real roots. Maybe z1, z2, and z3 are all real. So graphically what's going on? That's very easy. The polynomial will cut the x-axis 3 times, okay? All the roots are real. So for example, p of x could be x squared minus 1 right here. I'm going to try to make it simple, and x plus 2. Here we go. So we have x cubed plus 2x squared minus x minus 2. Here's an example of a polynomial with 3 real roots. So it's x plus 1, x minus 1, okay? Right here for this one. All right. Then what else can we have? We can have a polynomial here. Let me describe the behavior first. That has only 2 different roots, okay? Don't forget, you got to count them with their multiplicity. So there is a root of multiplicity 1 and a root of multiplicity 2 here. And if you count them with their multiplicity, you have 3. What kind of polynomial that may be? So that may be p of x equals, so let me take x minus 1, and here I'll take x plus 1 squared, okay? For example, I guess the picture is showing you the other way, so here we go, x plus 1 and x minus 1 squared. So what is this? This would be x plus 1 times x squared minus 2x plus 1. So it is x cubed. Where are my x squared? Right here. So minus 2 plus 1 minus 1 minus x squared. Where's my x? Okay, negative 2 right here and plus 1. So minus x plus 1. I think that's correct. So this is a polynomial with 2 different roots, but when you count them with a multiplicity, you have 3 roots, and they're all real, okay? And finally, there's another case where maybe here graphically, I'm gonna show you this one, where you only have 1 real root, okay? What about the other 2? Well, they will be complex, okay? So for example, p of x equals, so here's the quadratic irreducible, x squared plus 1, okay? You cannot factor that with real number, times, and I'm gonna say x minus 1, for example, okay? So this is, or if I wanna check that, it should be x plus 1, right? Because it looks like it could be minus 1 right there. So if I'm expanding this, I will have x cubed plus x squared plus x plus 1. So this is a polynomial with 2 complex conjugate roots, right? What are the roots? X squared equals negative 1, so x equals plus or minus I, right here, okay? And 1 real root. That's it for all the possible roots of the polynomial, okay? Let's talk about factorization now with example number 2. So this is an example I went over in lecture 44. We did factor it. Let me remind you of the factorization that we found. In lecture 44, I asked you to show that 1 plus 2i was a root of this polynomial. So I ask you to show that. We did a synthetic substitution and we factored this as x minus 1 minus 2i, okay, because it's a root right here. Then we had the complex root. All the coefficients are real, right? So complex roots come in pairs. So we had x minus 1 plus 2i right here. And then after we did our synthetic substitution, we found that the last factor was 3x plus 2. So here we go. Here's a factorization of f of x. This one, it is a factorization with complex roots. Now, how do you factor f of x with real roots only? Well, if you don't want to have these complex roots, okay, because after all, you start with something that only has real numbers, right, real coefficient, then multiply this right here. So you have x minus 1 squared plus 2 squared, right? Please remember, when you multiply a plus ib times a minus ib, it's a squared plus b squared, right? This is my a, this is my b. This is my A, this is my B, all right? Anyway, this is something you should remember. times 3x plus 2 right here. And so we have, so I'm going to expand this, so we have x squared minus 2x, then we have a plus 1 plus 4 plus 5 times 3x plus 2. That's it. This is how also I can factor my polynomial. You see, here's a linear factor right there, and here's a quadratic irreducible. You cannot factor this polynomial with real coefficient because the roots are complex. All right, so I'm gonna let you work on 3, and I want to go over another example which I did in class but a little bit too quickly to my taste. It's the last, I believe it's the last example, example number 6 from, again, lecture 44. Let me go back to lecture 44, example 6. All right, here it is. I did not do it in the video. I covered it in class, and it was a little bit too quick. It was at the end of class. So let's finish it right now, and I'm going to show you the 2 possible factorization for this polynomial, okay? So first of all, I'm asking you to find f of negative 1 plus I. So we're going to do a synthetic substitution right here, negative 1 plus I. And I know I'm going to spread my numbers a little bit because I'm dealing with complex coefficient right here, right? So 15, 6, and negative 2, I don't need to write a 0. They're all there. Okay? So let's do it, and you know how I do it, right? I know I can bring down the 4. It's easy to multiply by 4, negative 4 plus 4i. And then I can even add that easily, 8 plus 4i. But then, if I want to go back right here, I'm going to have to multiply this by this, and this is tedious. Therefore, I'm going to be using the calculator. We went over that in class, so let me go do it quickly. I'm storing this into a, so negative 1 plus second dot stored into a right here, okay? Then what do? I have to do times 4. That's the first time I go up, right? Times 4 equals that. You should have it in your note, okay? And then I'm adding 12. So again, that's easy to do by hand. But now I got to time this by negative 1 plus I. So that's what I called a, times a. And I find negative 12 plus 4i. Okay, what do I do with that? I'm right here right now. Negative 12 plus 4i. I'm adding 15, so it should be 3 plus 4i. So let's add 15 to it. Where am I? Right here. Plus 15 equals that, and then times a again, right? Times a, and we find negative 7 minus I. So here I have negative 7 minus I, and this is negative 1 minus I. And if you multiply this, do it with the calculator, please, but that would give you 2. We did it in class. I'm going a little bit fast. Okay, it's a 0. Therefore, its conjugate must be a 0 because all the coefficients are real. So now I'm going to do it again with negative 1 minus I. And this time, I know I don't need my calculator because it should all be very nice. Okay, so bring down the 4. Negative 4 minus 4i. You cannot have any complex coefficient right here, okay? 4, negative 4 minus 4i, that's negative 1. 1 plus I, 0, as expected. All right, so now where are we? We have that, let me see. We have that f of x is equal to, so the first root, negative 1 plus I, so x minus, so plus 1 minus I. Here we go, that's my first factor. Then the second root is going to be x plus 1 plus I. Okay, then what? Then that's a degree 2 right here, right? Times 4x squared plus 4x minus 1. Now 4x squared plus 4x minus 1, this does not factor. So what do you do to it? Well, you got to solve it. You got to find the zeros, okay? So 4x squared plus 4x minus 1 equal to 0. I'm going to complete the square. I'm going to divide by 4. X squared plus x minus 1/4 equal to 0. Sorry, x squared right here. X plus 1/2, right? And then, so minus 1/4 minus 1/4, that's minus 1/2. So equals 1/2. Please take your time, do it on the side. But anyway, x equals negative 1/2 plus or minus 1 over root 2. Now, I've asked you not to necessarily rationalize, but this one, I'm going to rationalize because I know where that's going, okay? So negative 1/2 plus or minus root 2 over 2. You'll see where that's going. Okay, so I have my two zeros of this one. Therefore, let's see how we can factor f of x. So I'm going to write that f of x is equal to x plus 1 minus I times x plus 1 plus I times what? Times x, then minus 1 of the two roots. So plus 1/2 minus root 2 over 2. I have to erase that, sorry. Okay. Times, finally, the last one, x plus 1 over 2 plus root 2 over 2. Now, don't forget, see, this factorization are coming from the root. You gotta check for the leading term. What's the leading term of your leading coefficient? What's the leading coefficient of f? The leading coefficient of f is 4. It's 4, okay? All right. What's the leading coefficient of your factorization? Well, it is just 1, so that's not going to work. I need to write a 4 right here. Now, the 4, what I do, it's okay. You can just stop right here. It's fine. But what I do with the 4 is 2 times 2, and I'm going to give one of the two to this factor, and the other one I'm going to give it to this factor. Therefore, I have f of x equals x plus 1 minus I times x plus 1 plus I times, now when you multiply this by 2, what do you have? 2x plus 1 minus root 2 times 2x plus 1 plus root 2. And this is your factorization of f with complex coefficient, okay? These two factors have complex coefficient. Now, what about if you don't want a factor with complex coefficient, but you're only looking for real coefficient? Well, you would have to multiply these two terms together, okay? And you would find f of x equals, so that would be x squared plus 2x plus 2, I believe, times 2x plus 1 minus root 2 times 2x plus 1 plus root 2. Okay, so I wanted to go over another example to show you the two ways to factor your polynomial function. In this one, there are no, in this factorization right here, you do not have any complex coefficient. They are all real. Thank you for watching.